Hello, and welcome to Simply About Earth, where curiosity thrives and science takes the scenic route to sleep. Tonight we sail far, beyond memory, deeper than history, to a world so old it's almost unrecognizable. It's not ancient pyramids, not dinosaurs, not even the first forests.
No, tonight we go back 2 billion years, to a time when Earth looked unfamiliar, when oxygen was new, when the continents were strangers, still learning to dance.
To a time when the sky might have looked pink, the seas green, and the land, well, there wasn't much land to speak of. Life was just learning to breathe, and in doing so, it destroyed almost everything.
But before we dive into the maelstrom of ancient oceans and alien atmospheres, I'm curious, where in the world are you listening from tonight? And if you look at your watch, what time is it? Strange, isn't it? A story of 2 billion years ago.
And yet here we are, sharing this quiet little moment across time zones and continents. If you find this a soothing way to unwind, a gentle nudge toward daydreaming, or simply a curious companion at the end of a long day, I'd be so grateful if you'd like the video or subscribe.
It helps this little circle of stellar science reach others who might also need a moment of peace. Now, I hope this isn't so captivating that it keeps you awake.
But if it does, well, at least you'll fall asleep with visions of volcanoes, microbes, and rusty iron skies. So settle in, slow down. Let's begin.
Because if you look far enough, past kings and empires, past extinction events and ice ages, you'll find Earth both ancient and alien. About 2 billion years ago, the air was poisoned, the seas teemed with strange bacteria, and yet something was happening.
Planetary transformation was already well underway, so massive that it changed the chemistry of the oceans, the structure of the atmosphere, and the fate of nearly all life. And somehow, some tiny, fragile glimmers of life survived.
But how? And what exactly was Earth like back then? Let's find out. Some stories begin with thunder. This one begins with a compass needle. It was a mystery you'd only notice if you were the kind of person who really pays attention to rocks.
The kind of person who looks at a rock outcrop and sees a timeline, not just a rock. In the late 20th century, a geologist was wandering through the Canadian Shield, a vast tract of exposed bedrock billions of years old, when something strange caught his eye.
He had a standard field compass, the kind that should obediently point north. But near a certain formation, it wavered, twitched, refused to settle. Now, a less curious soul might have written this off as a local anomaly, shrugged, and moved on.
But scientists are often professional questioners, and the question became, what happened here deep in the crust long before the continents looked anything like they do today? This question would echo through labs and universities, bouncing between mineral samples, magnetic studies, and isotopic analyses.
And slowly, a picture began to emerge, not just of ancient rocks, but of an ancient world. A world caught in one of the greatest planetary mood swings in Earth's history. A time when life nearly committed suicide by trying something new.
It's hard to imagine. 2 billion years ago is so far beyond the human scale that even the imagination begins to spin a little. To put it in perspective, if Earth's history were condensed into a single calendar year, humans wouldn't have emerged until the last hour of December 31st.
2 billion years ago, it would have been around mid-March, when the planet was just beginning to settle into its groove. The crust was thickening. Volcanoes were still raging in ways we don't see today. The moon was a little closer, the days a little shorter, the sun a little dimmer, and yet something was happening deep beneath the shallow seas and iron-rich waters. It wasn't always easy to piece this world together. The evidence was scattered.
Clues hidden in the banded iron formations, those striped rocks found on ancient seafloors where layers of iron and silica alternate like pages in a geological book. Some of these formations were massive, stretching for hundreds of kilometers. For a long time, they were simply there, beautiful, strange, and not entirely understood. But the more geologists dug deeper, the more they realized these bands were more than just rocks. They served as a kind of chronicle, capturing the chemical interactions between the oceans and the atmosphere. And during the period when these bands ceased to form, something fundamental changed. The planet seemed to switch to a different mode.
And the catalyst for this process were tiny, inconspicuous creatures, cyanobacteria. They weren't particularly impressive, and they still aren't. They were simply single-celled microorganisms, drifting leisurely in coastal waters and absorbing sunlight.
But they were destined to become the greatest transformers of Earth that ever existed. You see, these microorganisms had mastered a unique mechanism, something evolution had never attempted before. They could perform photosynthesis, but not the kind that simply metabolizes carbon.
This was an enhanced version, capable of splitting water molecules and releasing oxygen as a byproduct. Oxygen sounds like something useful, and eventually it became so. But at that time, it represented a danger, an undesirable, even deadly substance.
After all, the entire Earth's biosphere, all living organisms, evolved in an oxygen-free environment. And now, thanks to the quiet, bubbling respiration of microorganisms, this world began to change. At first, it seemed harmless.
Oxygen reacted with iron in the oceans, oxidizing it into insoluble compounds that settled to the seafloor layer by layer. This is how those banded iron formations formed, alternating phases of oxygenation and stagnation. But over time, the iron reserves depleted.
The oceans could no longer absorb oxygen, and it began to accumulate in the water, in the air, everywhere. Today, this phenomenon is known as the Great Oxidation.
This was not a sudden cataclysm caused by an asteroid impact, a volcanic eruption, or the emergence of a monster from the deep. Microorganisms simply breathed, day after day, century after century, filling the world with the gas that poisoned nearly all previously existing life.
But we're getting ahead of ourselves. In the present day, geologists were still piecing together the disparate evidence. There were other clues, too. Unusual sulfur isotope ratios in ancient rocks pointed to massive shifts in atmospheric chemistry.
Changes that don't just happen, they require a cause. William Martin, a biologist fascinated by the origins of complex life, pointed to molecular fossils, lipid residues, and chemical biomarkers preserved over eons. Other scientists, such as Donald Canfield, argued that oxygenation occurred in stages, unevenly, and was more complex than a single event. And each of them was probably right in their own way, because the Earth doesn't flip a switch. It breathes, it pulsates. Each oxygen age is periodically interrupted by a deoxygenation anomaly.
It changes with a rhythm, and we are still learning to read its history. One of the most astonishing discoveries occurred not in chemistry, but in texture.
In South Africa's Transvaal supergroup, a vast massif of ancient rock that has survived erosion, earthquakes, and time itself,
researchers discovered stromatolites. These layered mounds of sedimentary rock were formed by microbial mats, and in some cases they are still forming.
Modern stromatolites exist today in a few salty, secluded corners of the globe. But these fossils date back to a time before animals, plants, or anything with nerves, bones, or eyes existed. The shape and texture of these formations suggested a slow, patient life.
Microorganisms coexisted, building layer upon layer in sunlight, releasing oxygen, unaware that their metabolic waste was rewriting the rules of the planet. And it was here, standing on outcrops half a world away, gazing at rocks older than multicellular life, that modern scientists began to comprehend the scale of what had happened.
Not a war, not a catastrophe in the conventional sense, but a shift, a long, slow planetary sigh, a transformation so complete that it redefined the concept of habitability. For a long time, even telling this story was difficult.
Too many gaps, too few records, rocks that have been crushed, metamorphosed, or recycled back into the mantle. But science, like Earth itself, is persistent, and slowly, from sulfur and iron, from texture and isotopes, a picture emerged.
2 billion years ago, Earth was on the cusp of transforming into something new. We're used to thinking of oxygen as the giver of life. But too much oxygen is toxic to the wrong life forms. It burns. It corrodes.
It interferes with ancient biochemical pathways, and so the very gas that would one day allow animals to thrive began as a poison. And like many poisons, it didn't just kill, it changed everything.
The compass needle twitching strangely in the Canadian forest wasn't just reacting to minerals, reacting to ancient scars, records of magnetic shifts associated with atmospheric transformations, moments when the Earth literally changed its mind about how it wanted to rotate, breathe, and maintain equilibrium.
Sometimes uncovering the depths of the past is like holding a seashell to your ear and hearing not the ocean, but the echo of a world that once suffocated. A world where the sky at sunset could turn a delicate purple, thick with haze.
Where lightning struck strange chemical clouds, where the seas shimmered green and purple instead of blue, and in coastal waters, microbial mats quietly exhaled their invisible revolution. It's sobering, isn't it, to realize that Earth's greatest extinctions weren't always bangs, but whispers.
That the ground beneath our feet was once an ocean floor, rusted by the breath of life. That the atmosphere we take for granted, which we casually inhale before saying hello, was an unimaginable luxury for much of the planet's history.
And it all began with a mystery. A needle that refused to point north. A stone that weighed more than it should. A question that wouldn't go away. Because science, at its core, isn't just about answers. It's also about wonder.
The kind that follows a twitching compass through billions of years of history. To understand what Earth was like 2 billion years ago, you have to let go of everything familiar. Forget about trees. There were none.
No forests, no leaves, no roots to hold the soil, because there was barely any soil. And without plants, there were no flowers, no bees, no birdsong at dawn.
The land, scarce as it was mostly barren, harsh, sun-bleached, wind-battered, and shaped more by lava and weather than by life. There were no animals, nothing with eyes, ears, legs, or even a mouth, no worms burrowing beneath the surface.
No fish slithering through the water, no predators, no prey, only microbes. Trillions of them, invisible to the naked eye, but everywhere in the water, in the mud, clinging to rocks, forming films that lived, died, and built upon each other, like patient architects of a new world.
The oceans were vast, shallow in some places, deep in others. But they didn't sparkle blue as they do today. They could be green or even rusty red in certain regions, stained with iron and sulfur, colored by the metabolic waste of ancient life.
And the sky might not be blue at all. The idea of a clear, azure dome overhead is something we take for granted. But back then, the atmosphere was filled with volcanic gases and haze. Without the protective ozone layer, ultraviolet radiation would have been intense. The air would have had very little oxygen, perhaps enough to be dangerous to organisms that never evolved to cope with it.
Instead of the blue we know today, the sky might have appeared pinkish or orange in certain times of day, especially if methane was abundant. Some researchers believe sunsets might have been ghostly and otherworldly, casting colors we would have difficulty naming. The sun itself would have appeared slightly dimmer, its energy output a few percent lower than it does today. But that would have been enough to warm the planet, but only just. The continents themselves also look different.
Tectonic plates were still moving, slowly dragging land masses across the planet's surface. But the arrangement of the continents looked nothing like the familiar contours of today. No Americas, no Africa, no Asia, no Australia.
Instead, cratons, ancient fragments of continental crust, slowly drifted, colliding, forming supercontinents that eventually tore apart. One such supercontinent may have existed around this time. Nuna, also called Nunakubai by some Norkbogtitaigin geologists, was a largely barren landmass stitched together from the roots of future continents.
Little life existed there. Most of the action took place in the oceans. And in these oceans, something extraordinary was happening. Cyanobacteria, tiny, resilient, and incredibly powerful, were proliferating. Floating in mats, they formed stromatolites, layered structures built over generations. Each layer was a time capsule, a generation of microbes capturing sunlight, photosynthesizing, exhaling oxygen, and dying, to be buried beneath the next layer. These structures dotted the shallow coastal flats like microbial cities, and they worked slowly, very slowly. No tides of revolution.
Just a steady pulse of chemical transformation. They inhaled carbon dioxide and sunlight. They exhaled oxygen. At first, the oxygen didn't last long. It immediately reacted with the colossal amounts of dissolved iron in the oceans, oxidizing it into iron oxides, which precipitated out of the water and sunk to the sea floor.
It was this process that gave rise to the famous banded iron formations, rusted streaks in the geologic record, reminiscent of tree rings etched in stone. Over time, however, the iron reserves were depleted, leaving the oxygen with nowhere to go.
That's when the planet began to transform. We have no precise idea of what it would have been like to be on Earth at that time, if it's even possible to talk about sensations.
There were no eyes to see, no lungs to breathe, no tongue to describe what was happening. But we can infer that temperatures were likely higher, at least in some regions. Greenhouse gases like methane and carbon dioxide were abundant, creating a powerful atmospheric blanket.
Yet paradoxically, it's possible that as oxygen concentrations increased, the climate became less stable. Methane, one of the most potent greenhouse gases,
reacts with oxygen. And as cyanobacteria continued to release more oxygen, methane was removed from the atmosphere. Reduced methane concentrations meant less warming.
And so, suddenly, by geological standards, the planet could have plunged into an ice age, a severe one at that, perhaps even a global one. Some scientists believe this period triggered one of the earliest snowball Earth events, when ice reached the equator, turning the planet into a frozen ball drifting through space.
Others believe the situation was less extreme, more like a slush Earth, where equatorial waters remained unfrozen, but vast ice sheets advanced further than they do today. Either way, it was a massive shift, and for life, it was catastrophic.
Most anaerobic organisms, those that thrived without oxygen, now suffocated in it. Their ancient metabolic processes, honed over billions of years in anoxic conditions, couldn't cope with the new environment. Many were poisoned by the very air. Others starved as food sources disappeared.
Imagine a world where your breath is toxic, where your energy source disappears, where the oceans become hostile. That was Earth 2 billion years ago. Not in flames, not in chaos, but quietly transforming in such a way that only a few life forms could survive. And yet, some did. Some bacteria evolved to cope with oxygen, to detoxify it, to utilize it, and even to harness its incredible chemical energy. Oxygen, it turned out, was efficient. Far more efficient than the chemical energy systems that had existed before. Thanks to it, life could become larger, more complex, bolder, but not immediately. In those days, life remained simple, primarily prokaryotic. Cells without nuclei, no plants, no fungi, no animals, only microbial life, drifting, clinging, spreading.
Some began to work together, forming colonies, perhaps even experimenting with cooperation in their own tiny world. However, the revolution of multicellularity occurred hundreds of millions of years before. The oceans were likely stratified, meaning they had distinct chemical layers. The upper layers, exposed to sunlight, were saturated with oxygen. The deeper waters remained anoxic, rich in hydrogen sulfide, methane, and other ancient compounds. If you had a time-traveling submarine and dived, you would pass from breathable water to a realm that smelled like rotten eggs and felt like diving into an alien soup.
Some sulfur-producing bacteria, such as purple sulfur bacteria, thrived in this twilight zone, just below the reach of oxygen, just above the lifeless abyss. They could create shimmering, colorful blooms, their pigments tinting the water with strange, iridescent hues. An ancient ocean rainbow, invisible to the eye.
Above them, the surface shimmered in the weaker sun. There were no coral reefs, no schools of fish darting through kelp beds, only microbial mats gently rocking in the currents. No tides as we know them, no waves crashing against populated shores. Just a quiet world, slowly exhaling, slowly evolving. Geologically, the Earth was restless. Volcanoes were common. Magma rose through the crust, creating new land, releasing gases, stirring the atmosphere. The balance between carbon dioxide, methane, sulfur, and now oxygen was delicate, complex, and constantly shifting. Thunderstorms were perhaps more frequent, not because the Earth was angrier, but because the atmosphere was thicker, denser, charged differently.
Every lightning strike, a brief, bright rift in the sky, was a reminder that even in this quiet world, power was everywhere. During that period, the Earth rotated slightly faster than it does today. Days were shorter, roughly 18 to 20 hours long.
The moon was closer, the tides were higher, and the planet was still recovering from the tumultuous birth of billions of years ago. This was Earth in transition. Not yet the blue pearl we know, but not the hellish molten sphere once was.
It was something in between, raw, quiet, patient, and it was setting the stage for everything that was to come. The Great Oxidation didn't just poison the atmosphere. It laid the foundation for respiration, for complex chemistry, for the future.
Oxygen that once killed would one day allow muscles to contract, brains to sparkle, hearts to beat. But that future was still so far away it barely glimmered on the horizon. At that time, Earth was simply becoming itself.
We often imagine transformation as noisy, dramatic, explosive. But sometimes the most profound changes happen slowly, imperceptibly, one breath at a time. Such was Earth 2 billion years ago. The atmosphere was thin and dangerous. The land was mostly naked.
The oceans were layered, colored, and alive in ways we can barely comprehend. The surface teemed with microbes we would need a microscope to see, if we could even survive long enough to hold it steady. There were no eyes to see this world.
No songs to mark its passing. But it was real, and it was the beginning of something extraordinary. The planet was learning to breathe. By now, the story seems almost peaceful. A slow-breathing world of microbial mats and quiet chemical changes, drifting beneath ancient skies.
But this calm is deceptive, because beneath it, something enormous was brewing. The Great Oxidation was not a single explosion. It was more like a rising tide, gradual, persistent, unstoppable.
Oxygen began as a trace gas, a background whisper, quickly consumed by the ocean's hungry iron. But eventually, inevitably, it outpaced its invaders, and when it did, it broke free. The accumulation of oxygen in the atmosphere ushered in a biochemical revolution.
For billions of years, Earth had been an anoxic planet. Life thrived without oxygen, fermenting, reducing, recycling. But cyanobacteria developed a trick so powerful it would flip the whole scenario. They could harvest sunlight and use its energy to split water molecules.
And, in doing so, they released oxygen. Free oxygen, a radical new element in the planetary system. At first, this oxygen didn't stick around. It was too reactive. It slammed into iron, sulfur, methane, anything it could come into contact with.
The oceans were full of ferric iron, and oxygen clung to it like a magnet, oxidizing it into insoluble rust that rained down to the seafloor. This process continued for millions of years. Oxygen in, rust out, again and again, until the iron was almost gone. And then came the tipping point. Oxygen had nowhere else to go. It began to accumulate in the atmosphere, first in faint traces, then in measurable quantities.
And life, at least, life as it existed then, was not prepared. Anaerobic organisms, the dominant life forms for 2 billion years, were not just unadapted to oxygen, they were vulnerable to it.
Oxygen, for all its benefits for modern metabolism, is also toxic in high concentrations. It creates reactive oxygen species, molecules that damage DNA, rupture membranes, and interfere with fundamental biochemical processes.
What we now call oxidative stress was a death sentence back then.
Oxygen was an uninvited guest at a party that was doing just fine without it. The reaction was catastrophic. Entire microbial ecosystems collapsed. Sulfate-reducing bacteria, methanogens, and other anaerobes retreated to the few remaining anoxic pockets deep in the ocean, buried in sediment, hidden in rock crevices.
Others died out entirely, a global extinction, not by fire or impact, but by respiration. But this new gas didn't stop at biology. It attacked the atmosphere itself. Oxygen collided with methane, the planet's dominant greenhouse gas, and began removing it.
Methane, though only a small component of the atmosphere, was incredibly efficient at trapping heat, far more efficient than carbon dioxide. This is why Earth remained warm despite the sun's weaker output. And now, with methane waning, the planet began to cool.
The geological record from this period shows a sharp drop in temperature. Glacial deposits, specifically till, are found in ancient rocks on multiple continents, indicating widespread, perhaps even global glaciation.
This may have been the first true snowball Earth scenario, with the world frozen from pole to pole. The oceans were sealed under thick layers of ice, and equatorial regions were shrouded in frost.
This phenomenon was caused by chemical processes, and the result was climate change driven by a chain reaction. It all goes back to tiny cells absorbing carbon dioxide and releasing oxygen.
It's strange to think of photosynthesis as a weapon, but in this context, it is. Life turned on itself. By inventing a new way to survive, cyanobacteria inadvertently rewrote the rules of existence.
Not because they were aggressive or evil, those are human notions, but because evolution rewards what works, not what is safe. And photosynthesis worked. The oxygen it released not only altered the chemistry of the air and water, but also altered the behavior of the planet's surface itself.
With the advent of oxygen in the atmosphere, new types of weathering began. Rocks broke down differently, and soils began to form in more complex ways.
The carbon cycle, the vast planetary system through which carbon moves between air, land, ocean, and life, became more complex. With oxygen, new chemical pathways emerged. Some carbon was buried as organic matter, some released as carbon dioxide.
But always, the presence of oxygen altered the rhythm of things. Deep in the ocean, changes were also taking place. The layered structure of water, oxygenated from above and below, began to shift. Nutrient availability shifted. Microbial ecosystems reorganized.
Some species adapted, finding ways to detoxify or even utilize oxygen. Others vanished, leaving behind molecular fossils and chemical ghosts. And above all, the sky was changing. Before the Great Oxidation, the atmosphere was saturated with methane and hydrogen sulfide.
The air may have had a reddish tint, tinted by organic aerosols, but as oxygen rose and methane fell, the haze dissipated. The sky may have acquired a blue hue for the first time.
Not the deep azure of today's skies, but a softer, paler shade. Nevertheless, it marked a turning point. The planet, once suffocated by gases, began to breathe cleanly. Not comfortably, not yet, but differently. And finally, something new emerged.
Ozone. Ozone is just 3 oxygen atoms bonded together, but it is vital. It absorbs ultraviolet radiation, protecting life on the surface from harmful rays. Without ozone, the Earth remains hostile. With it, the surface becomes habitable.
And although true terrestrial life was still far in the future, the building blocks were now being laid in the stratosphere by the invisible hands of chemistry. The Earth wasn't simply cooling, it was evolving.
And all of this, every ice sheet, every dying cell, every change in the atmosphere, all of it was due to the respiration of microbes. Greenland's Irla Greenstone Belt, some of the oldest rocks on Earth, preserves evidence of this transition.
Tiny inclusions, carbon isotopes, sulfur signatures, all whisper the same story. Oxygen rose, life suffocated, the world changed. Further south, in South Africa and Western Australia, researchers found similar clues. Redstone deposits, oxidized soils dating to this era.
Their color is a product of the reaction of iron with free oxygen. On modern Earth, we associate this rusty red hue with deserts or canyons. But back then, it was a sign that the air had changed. Fossils from these times are rare.
Life was small, soft-bodied, and reluctant to leave traces. But geochemistry became the new fossil record, and it told a clear story. A tipping point had been reached. The system had flipped. Oxygen had taken over, and it was not going away.
What followed was not a smooth progression toward the world we know. There were setbacks, reversals, perhaps even secondary extinctions. Oxygen levels rose, then fell, then rose again. The climate shifted. The biosphere struggled to overcome new challenges.
But a long arc of change had begun, and at the core of it all, the same mechanism always remained. Life changes the planet, simply trying to survive. The air was no longer invisible. Not quite. It shimmered with consequences.
You couldn't see oxygen accumulating in the atmosphere 2 billion years ago, but the planet felt it. Earth's chemistry had shifted, its mood had changed. A world that had been chemically predictable for eons suddenly became unstable, reactive, restless.
And this restlessness didn't stop at the surface. It moved down into the rocks themselves. Buried in ancient sediments, geologists detected a sharp signal, the so-called sulfur isotope anomaly.
For millions of years, sulfur had circulated through the environment according to a specific pattern shaped by volcanic activity and microbial processing. But then, suddenly, this pattern broke. The anomaly disappeared. The sulfur cycle had changed, and the only plausible explanation was rising oxygen levels.
It was everywhere, not yet dominant, but pervasive, like a scent that lingered even after a door was closed. And with this rise, strange new feedback loops emerged. Oxygen wasn't just removing methane from the atmosphere, it was also interacting with volcanic gases.
Sulfur dioxide, carbon monoxide, hydrogen, all reacted differently in this new oxidizer world. Volcanic eruptions began to alter the climate in new ways, contributing not only to warmth but also to cold, depending on the aerosols they released. Clouds formed differently.
Rain fell with new chemistry. The water cycle itself shifted subtly, shaped now by an atmosphere that carried traces of ozone, free radicals, and acids. Meanwhile, in the oceans, life continued its quiet rebellion.
Cyanobacteria thrived in the upper euphotic zones, those sunlit layers near the surface. But as oxygen accumulated, it began to push downward. The deeper layers of the ocean became unstable. Hydrogen sulfide, once abundant, began to decline. Anoxic zonas shrank. New gradients formed.
And in these gradients, evolution found new niches. Some microbes developed antioxidant enzymes, superoxide dismutase, catalase, molecules designed to neutralize the damaging effects of oxygen. Others retreated to safer corners of the biosphere, deep-sea vents, muddy sediments, oxygen-depleted pools where chemistry hadn't yet caught up.
Some, surprisingly, learned to harness the power of oxygen, not just detoxify it, but utilize it. This was just the beginning, a barely audible whisper of aerobic respiration. The mathematics of it is astounding. Anaerobic processes like fermentation are slow and inefficient limited.
But aerobic respiration produces far more energy per unit of fuel. With it, life could grow faster, build larger structures, and perform more complex tasks. But this advantage wouldn't be fully realized for hundreds of millions of years.
For now, it was merely potential, like a match lying next to dry wood, waiting for a spark. And while all this unfolded in the shallows, the planet's surface continued its slow tectonic ballet. Supercontinents shifted, cratons collided.
The Earth's crust thickened in places, forming new mountain ranges. Subduction zones recycled oceanic plates into the mantle, exposing surface materials to intense heat and pressure.
And the deep carbon cycle, the one that governs the exchange of carbon between the Earth's surface and its interior, was altered by these new oxygen-rich conditions. Minerals began to behave differently. New ores formed. The very composition of the Earth's crust changed.
Even the core may have reacted. Some models suggest that the crystallization of Earth's inner core, solidifying within the liquid outer core, may have been influenced by changes in the planet's overall oxidation state. As above, so below.
Even in the deepest parts of the planet, echoes of oxygen could be felt. And through it all, life endured, battered, diminished, stymied, but never completely vanished.
When the conditions of the snowball Earth eventually eased, whether after millions of years or through periodic thawing and refreezing, survivors emerged into a world that had been irreversibly altered. New rules emerged in the atmosphere. The oceans contained new nutrients. The energy balance shifted.
And though it would take eons for multicellular life to emerge, the foundation was laid not by force, but by breath. Oxygen did not come as a blessing. Not immediately. It swept in like a silent invader. It choked, poisoned, and oxidized.
It disrupted the climate and froze the seas. But it also opened doors that had been closed. Doors to complexity, to energy, to change. It has created crises, but also opportunities. This duality will forever define oxygen. Even today, it is simultaneously essential and dangerous.
We breathe it constantly, yet it ages us, damages our cells, slowly wears us down. It gives us fire and rust, metabolism and decay. It is simultaneously a giver of life and a slow thief.
And it all began here, in the breathing shallows of a world still sorting itself out. This page of Earth's history is written not in bones, teeth, or shells, they will appear later, but in chemistry, in rock layers and isotopic shifts, in the color of ancient sediments and the fossils of ancient metabolism.
It is a story told not through form, but through process,
and at its core always lies the quiet revolution of photosynthesis. What began as a small evolutionary adventure has become the engine of planetary transformation, and not just on Earth.
Scientists believe that oxygen may be one of the few truly universal biosignals, something we might discover on exoplanet if photosynthesis evolves elsewhere in the cosmos. That's how far the circles stretch, from a single blue-green microbe to an entire world.
And we're still learning more. New discoveries emerge every year. New geochemical models, new microfossils, new theories about the pace and consequences of this great oxidation. Some argue it was a single sharp upsurge. Others see multi-stage evolution.
Perhaps there were pulses of oxygenation, each shaping the biosphere in new waves. Others point to feedback loops involving methane-producing microbes and volcanic eruptions. This story is still being written, but what remains constant is that 2 billion years ago, Earth turned a corner.
It didn't do it with noise or drama. It did it with microbes and sunlight, with chemistry and time, with breaths that echo it across the ages. And hidden in that breath was the future.
Not just the oxygen that would one day fill the lungs of trilobites, dinosaurs, and astronauts, but the promise of what life could become. Resilient, intelligent, and curious enough to dig into ancient rocks and ask, what happened here?
When you change the air, you change everything. At first glance, the story seems to end with rising oxygen levels, falling methane levels, and life entering a new regime. But the truth is, that was only the beginning.
Because the great acidification didn't just change Earth's chemistry. It set off a complex web of consequences that rippled through every layer of the planet, from the crust to the clouds. To imagine the consequences, imagine a quiet world suddenly learning a new language.
Every process that was once stable, weather, erosion, the carbon cycle, energy flow, microbial metabolism, now had to adapt to a completely different scenario. And as with any radical redesign, the first drafts were sloppy. Let's start with the oceans.
For billions of years, they served as the planet's chemical warehouse. Warm, iron-rich, anoxic, they were busy, full of microbial activity and deeply stratified. But now, as oxygen penetrated the shallows, their vertical structure began to change. This delicate layering of oxygenic surfaces and anoxic depths became unstable. The gas balance was disrupted, nutrient pathways were destroyed, entire ecosystems collapsed. It wasn't just the oxygen, it was the cascade it triggered.
Methanogens, those ancient microbes that once filled the atmosphere with methane, were retreating. Their habitats were disappearing. The niches they had occupied for eons suddenly became toxic.
The methane they produced had once enveloped the Earth in warmth, serving as an important buffer against the weak young sun. Now it was being destroyed, faster than it could be produced. As a result, the Earth began to freeze.
Glacial deposits from this era are found in rocks scattered across ancient cratons in Canada, South Africa, and Australia. These are not subtle local freezes. These are deep, widespread layers of tillite, a rock formed from compacted glacial debris.
In some places, there are boulders, rocks carried by icebergs and then deposited in soft ocean sediments as the ice melted. This is the kind of fingerprint you get only from a world that's suddenly iced over.
We don't know for sure how global the glaciation was. Some models posit a complete snowball Earth, an icy shell extending from pole to pole, turning the planet into a sparkling white sphere. Others favor a slush ball model, where the equatorial regions remained at least partially exposed, preserving a thin ribbon of liquid water for life to cling to. But either way, the planet was forever changed. After all, climate isn't just weather spread out over time. It's the sum of chemical feedback loops, solar energy balance, planetary albedo, and atmospheric composition. And all of it was changed. The new oxygen-rich air contained fewer greenhouse gases. The veil that once trapped heat disappeared. Clouds were transformed, perhaps becoming brighter and more reflective.
Even the ice-bound oceans now reflected sunlight back into space rather than absorbing it. It was as if Earth had accidentally discovered its own thermostat switch, and life was forced to adapt. Some organisms disappeared entirely.
Others survived, sheltered in ecological niches, hydrothermal vents, brine pools, deep sediments. These places remained warm, chemically buffered, protected from the new breath of the sky. Here, the old rules still applied. Here, anaerobic metabolisms could persist.
But beyond these refuges, everything else had to adapt or perish. Microbial mats changed their composition. New layers formed on top of old ones. Metabolic pathways evolved under pressure.
The emergence of antioxidant enzymes marked a silent arms race against the growing presence of reactive oxygen. Cells that once thrived in calm chemical orders now had to defend themselves against molecular instability. Even basic reproduction had to change.
DNA is fragile in the face of the wrath of oxygen. Organisms had to invent molecular tools to repair oxidative damage. Some of the earliest versions of modern DNA repair enzymes likely evolved during this era.
Not because life wanted to become more complex, but because it needed to become tougher. And yet, the Earth continued to rotate. As glaciers slid across the continents, they transformed the land. They crushed mountains, excavated valleys, and transported sediments far from their origins.
They exposed new rocks to the elements, which in turn altered weathering patterns. As fresh rock was weathered by rain and atmospheric carbon dioxide, more carbon was extracted from the atmosphere and stored in sediments.
This further cooled the planet, creating a feedback loop with no easy escape. Eventually, of course, the planet would thaw. Volcanoes never stopped erupting, after all.
Over time, their CO2 emissions accumulated in the thin air, and because the surface was encased in ice, the rate of weathering slowed, slowing the absorption of carbon.
And the life that remained carried the memory of the crisis in its molecules. But the story didn't end with survival. It began to lean toward possibility. Because once the immediate chaos of the Great Oxidation had subsided, once oxygen levels stabilized and the climate regained some equilibrium, something remarkable began to happen. New ecological possibilities opened up. For the first time, Earth had an atmosphere capable of supporting aerobic respiration.
This was a game changer. More energy meant more work could be done within each cell. More work meant greater complexity, new structures, new behaviors. It would take time, a long time, hundreds of millions of years before anything resembling multicellular life emerged.
But the first domino had already fallen and oxygen had pushed it forward. However, the Earth was not yet finished changing because, along with these biological changes, geological ones occurred. The oxidation of iron-rich minerals created entire new classes of ore deposits.
It's subtle, complex, and debated,
But like so many things in Earth science, everything is interconnected. And despite everything, the color of the sky has changed.
It's not easy to reconstruct the color of the ancient sky. We can't seal the air of 2 billion years ago. The news editorial team reports, by studying the composition of the atmosphere, including methane, carbon dioxide, nitrogen, and oxygen, scientists can reconstruct how light scattered in ancient times.
Before the advent of oxygen, the sky likely had a yellow-orange hue, reminiscent of the hydrocarbon haze on Saturn's moon Titan. However, later, with the formation of the ozone layer and the decline of aerosols, the atmosphere began to scatter shorter wavelengths of light.
This is how blue emerged, at first subtle, then increasingly saturated. The sky took on its familiar appearance, but at the time there was no one to see it. There were no eyes, no faces turned heavenward, no minds capable of admiring color.
There were only microbes, drifting, dividing, and surviving. Billions of years will pass before anyone can look back on this moment and call it what it truly was, a planetary reset. The world, reborn after the cooling, was cautious. Oxygen didn't flood the planet instantly.
It permeated gradually, rising in waves, sometimes retreating, sometimes advancing. It may have taken hundreds of millions of years before its concentration reached even a fraction of what we breathe today.
But it was enough to continue altering the biosphere, ensuring that the damage was done and opportunities opened. Oceans, once teeming with methane and hydrogen sulfide, gradually changed their chemistry. Oxygenated waters brought with them new minerals, new solubilities, and new balances.
Some regions saw a thriving proliferation of new microorganisms, while others became strangely still, turning from thriving anoxic basins to barren silt. And with the arrival of oxygen, something unusual appeared in the deep sea: phosphorus.
It's one of the most essential elements for life, but its behavior depends on the oxygen content of the water. In anoxic environments, phosphorus tends to bind tightly to particles and sink to the bottom, becoming unavailable.
However, in oxygenated waters, it remains more bioavailable, making it easier for living organisms to absorb. More phosphorus meant greater productivity, greater biomass, and more carbon for burial. And the more organic carbon buried, the more oxygen remained in the atmosphere, creating another feedback loop.
The system sustained itself. This may explain why the Great Oxidation Event was not a one-time event, but rather a slow, progressive process, a cycle of advance, collapse, and recovery, with each fluctuation leaving behind a slightly more oxygenated Earth.
It was not a smooth process. There were crashes, dips, and possible reversals. In some periods, oxygen could almost completely disappear from the air, displaced by volcanic gases or methane emissions.
Deep in the genetic memory of surviving microbes, traces of this revolution can still be found. Genes for resistance to oxidative stress, enzymes that would have been useless in an oxygen-free world.
Even the earliest versions of mitochondria, the tiny organelles that would one day power animal cells, could have arisen here, in this cauldron of oxygen and adaptation.
Over time, this bacterium evolved into a mitochondria. It's a familiar origin story, but back then it was just another risk in a world full of dangers.
This risk would eventually lead to the emergence of complex cells, eukaryotics capable of building tissue, forming organs, and writing poetry. But that was still far in the future. For now, Earth remained microbial, its drama quiet,
its actors small, but the stage was set.
The consequences of this event were not localized, but reverberated throughout every system. New minerals began to appear in the lithosphere, the rocky shell of the planet. Geologists have recorded a significant increase in mineral diversity after the Great Oxidation Event. Before the advent of oxygen, there were less than 1,500 different minerals. Afterward, there were more than 4,000. Why? Because oxygen is reactive. It forms new compounds, binds, breaks down, and recombines. It creates color variety and complexity.
Even gemstones were born in this new world. Many of the vibrant colors we associate with minerals, reds, greens, blues, are the result of oxidation. Earth's palette expanded simply because the air changed. Ozone continued to accumulate in the atmosphere, and with it came protection.
Ultraviolet light, once a deadly force that sterilized any soil it touched, was now filtered more effectively. It's likely that some ultraviolet light did penetrate. The news editorial team presents an analysis of the early stages of Earth's atmospheric formation and their long-term consequences.
Ice ages had occurred before, but those triggered by the rise of oxygen were different. They involved new dynamics, a new tempo, and a new chemistry. Some models suggest that entire glacial cycles changed their frequency after this event, as atmospheric composition played a more complex role in Earth's energy balance. Even the magnetosphere, the magnetic shield protecting Earth from solar radiation, may have responded in subtle ways.
It's a hypothetical connection, but worth considering. When the air changes, even the planet's invisible defenses can shift. And of course, there was time. Not just geological time, but evolutionary time. The pace of evolution is hard to measure. It doesn't tick like a clock.
They didn't take over the world immediately. Simpler life forms continued to rule for another billion years, but the signal had been sent. Complexity became possible, and with it, potential diversity. It's strange to think that death made this possible, that entire branches of the tree of life had to wither so that others could grow. But that's how ecosystems work. Extinction makes room, it resets conditions, it forces invention. And invention, however slow, is inexorable, and the world adapted in its own way.
Microbes didn't just survive, they thrived in the new oxygen gradients. Some became mixotrophs, utilizing both oxygen and anaerobic processes. Others retreated to stable niches, deep sediments, anoxic pools, hot springs. These refugees would preserve ancient metabolisms for billions of years.
Even today, you can find them in the Black Sea, in deep ocean trenches, in the guts of cows, tiny echoes of a pre-oxygen world. And the geological record, too, preserves its memory.
Shells rich in organic carbon, red layers stained with oxidized iron, traces of fossilized microbial mats dancing in shallow tides. Even the rate of sedimentation changed. New types of clays formed. Carbonates changed in composition.
The planet was writing its own autobiography, page after page, using tools it had never used before. And no one was watching. No intelligence, no culture, no myths, just a planet becoming something new. Every breath of oxygen whispered a different future.